So thank you for that introduction, Byron. For those of you that already know me, welcome. Very happy to have you all here today. For those of you that don't, if you'll indulge me, I want to use the knowledge that I've accumulated over the years to try and change the way that you think about some things. And in order to do that, we're going to go on a little bit of an adventure together, something different today. And to set the scene for this, I'm going to play you a video.
Reports that say that something hasn't happened are always interesting to me because, as we know, there are known knowns. There are things we know we know. We also know there are known unknowns. That is to say, we know there are some things we do not know. But there are also unknown unknowns, the ones we don't know we don't know.
So this is a quite famous short speech from Donald Rumsfeld back in 2002. And as he so eloquently explained there are things that we are currently not even aware of that we don't know. Right? And I've got a little diagram here of how to explain that, right? So if we start off on the top right-hand corner, these quadrants are going to form the basis of everything I'm going to talk to you about today. Start on the top right, facts. There's things that we know. And then we move around, and I've got a couple of slides. Actually, no, I don't. So known are the facts, known unknown are questions, unknown is exploration, and then we've got that final quadrant there. And I'll ask you all to have a think about what unknown knowns might be. Develop your own idea before we arrive at the end of this presentation. So in order to make things a little bit fun today, we're going to do it a bit different. Like I said, we're going on an adventure. We have our construction connect adventure, and for all means and purposes, this is you today. And our adventurer is going to start off with the first part, the most obvious, the known knowns. And I must apologize for anyone that came today wanting me to talk about the basics, the known knowns, the Australian standards, the NCC, our best practice guides, and so on. I'm not going to be talking about that in this particular presentation, but I needed to set the scene, right? So straight away we're going to go into our known unknowns, right? These are the questions that you might have, what's happening with the NCC, everything like that. These are the things you're already aware of, and regrettably, I'm not going to answer any of those questions either, but I will touch on it just very briefly because it has been discussed already today. NCC is still in a little bit of a state of limbo, freeze, don't freeze. We've had a little bit of advice on that, but yeah, nothing solid just yet. You might also have questions around how do we handle falls, what's the difference between fall requirements in domestic areas and residential areas and commercial wet areas, because there are substantial differences in the way that you read the code, even though these are all wet areas. These might be some things that you already have questions on. But unfortunately, I'm not going to talk to you about any of those either. We're going to be jumping straight into unknown unknowns. And what I'm going to try and do here is enlighten you on some things that I've seen that you maybe haven't had exposure to yet, and they'll arm you in your future adventures. Right, so to start things off, we're going to have a look down into our pit of spikes here, and our first trap is basement design. So we're going to talk about a couple of things on basement design before we move up throughout the building. So we'll have a look down, and our first topic is hydrostatic pressure. Probably a term that a lot of you are familiar with. It's the reason why basements leak most of the time. And it can cause some pretty significant issues on a building. Nice simple diagram here shows how that water, in this case from actually ground level, presumably rain or else other surface runoff, has actually infiltrated down and is starting to build up. And water has weight, quite a lot of weight in fact. And when you allow it to bear against a structure, you start to get these sort of issues. Right, that's a block wall. Another very similar one here as well. Four-foot block wall just buckling in internally. And you all might have seen these sort of structural failures. I'm going to talk to you about a very unique type of failure that I'd come across surprisingly about 4 or 5 times in the last 12 months. This exact same scenario has occurred, or a very similar variant of it. And I'll explain how it went about. So we had a project with a shoring wall, right? And this varied between projects. Some it was a secant pile wall, others it was a diaphragm wall, others it was a CSM wall. Anyway, it was a shoring wall. And the geotech engineer said, hey guys, like here's our report, we've done all our analysis, everything like that. You've got a problem with water on the outside. But look, I see on your structural diagrams that you've got this type of wall, like secant, for example, that they should be actually able to withstand hydrostatic pressure and stop the water coming in. Right, so here's a nice little diagram there. This is what should happen. We've got our okay, now I need the pointer. Got our shoring wall here, and water should not be able to infiltrate past it. The builder at the time said, that's awesome, that's the exact advice we want to hear. Now we can just sort of do, whatever we want. We've got water taken care of, right? What actually happened was this. Oh, and I should mention that there was actually, to tidy up the look of that wall in front, there was a 70mm shotcrete wall, which is the darker color here, applied in front. And actually, for good measure, on some of these, the builder even added in some water stops at junctions, and they added an additive to make the shotcrete watertight, right? So there was effort there. But what actually happened was this. No one bothered to or did the appropriate due diligence to talk to the shoring wall contractor and ask them if they were, because there's a big difference between what something can achieve and building it to achieve that on site. Differentiating factors between the type of soil and how well it retains your piles and everything will create a varying confidence. And what you'll find is a lot of shoring contractors wouldn't give a warranty for certain types of shoring walls, but that check wasn't made. There was no warranty or accountability. It was all optimism, which was pushing this. So what actually ended up happening was water was able to infiltrate, very slowly actually, through this wall. And then hydrostatic load ended up being applied to our shotcrete surface here. And hydrostatic pressure can build up one drop at a time. But as it does build up, this is what's happening, and this is what it looks like. Now, the only reason that this shotcrete wall didn't completely fall down was that the amount of water which was weeping through here and onto our floor area here was enough to release the hydrostatic pressure at the same time it was building up towards the critical point. So that's the only reason that this failure actually didn't occur. And really it just comes down to that due diligence on making sure that every party is accountable. And I will give you some key takeaways in a moment. But I do have another point about basements. And before I talk about that, we'll check in on our intrepid adventurer here, right? And what you're seeing here, adventurer's in a temple, he's solving a complex Mayan puzzle, right? And that's hard enough as it is, but he's also doing it underwater and holding his breath at the same time. What does this relate to in construction? It's this. This is a basement design, has a diaphragm wall, and there's water absolutely streaming in through all the anchor points around. So what does, if you imagine the waterproof is going to start at the bottom, and they're going to work their way up, right? You see that water running down the wall there. Basement tanking systems, as I believe Ross covered before, there's a lot of great products out there, but they do require skill and finesse to install. I strongly encourage you to talk to the sponsors, by the way, about the systems they offer this, and I think they'll all second this, is that they do work extremely well if you're able to install them correctly and effectively. And if you have water running down a wall that you're trying to anchor and terminate into, then you're not going to have a very fun time. Imagine trying to roll out a sheet membrane or even apply a liquid into this sort of pond here. This is the sort of situation that you get. We have water on top of this sheet membrane. We have water underneath. They're trying to simultaneously pump out above and below while maintaining all these joints that are bonded together there. without having correct consideration of dewatering, you're really going to have a bad time, and there's actually no way you can achieve a confidence-inspiring installation. Let me give you a few more examples. For those of you that don't know what this is, I'll explain. The red stuff is a swallowable water stop. That is supposed to be up on the wall there, above the injection tube. That has since fallen down and swollen and activated prematurely because of the amount of water which was coming down the wall. Now, whether the waterproofer should have even tried to install in that scenario is a different conversation, but you can see that these are the results. I'm not just saying it's hard, I'm saying it's practically impossible. Explain what's going on this one. So this is a pit. Steel's been installed, concrete's ready to pour. This was actually the day of the pour. I was asked to come out and have a look at final sign-off before the concrete gets poured, and what do I find? See down here? All the way along there, that's a massive cut in the membrane. It's not a loose weld, it was a cut. And this was placed there with the intention of putting down a pipe, sucking out the water from behind the membrane, and then also simultaneously trying to suck out the water on top of the membrane. I had best intentions, but it was just too hard. And they, to my understanding, just went ahead and poured this. There's no practical way to get in there, even if we were able to get the water out, to get in there and repair that cut that was used for the purpose of dewatering, because a dewatering system wasn't put into place in the first place. So just to summarize that quickly, how do we prevent this? Well, at the risk of oversimplifying it, it's two things. It's expertise and accountability. Expertise, by what I mean by expertise, is not considering dewatering as an important aspect and not considering the structural integrity of a shotcrete wall if we know there's going to be hydrostatic pressure against it, or not getting due accountability from the shoring contractor to make sure that it's going to actually work as we intended. Those are the things that prevent this, and they're actually kind of simple to do, right? Like, it's a few conversations during the design stage, but it's the knowledge that these could go wrong that will arm you with the ability to have these conversations. So that's all I have for basements at the moment. Our adventurer is now out of the temple and they're up on a cliff face. He's clinging to the edge of the cliff for his life, and the bird's attacking his fingers while he's holding on for dear life. This detail is a termination of the waterproofing membrane into reinforced concrete wall or block wall or whatever anyone else decides on site, right? This is the membrane holding on for dear life onto the structure so that it doesn't peel back and delaminate, or water isn't able to bypass it, get underneath the membrane, which then defeats the whole purpose of even having a waterproofing system, right? And this detail, you're probably quite familiar with this, is straight out of the standard. This is actually considered the most robust. I would say at least once a week, I get a call saying, do we have to do this? It's too hard, it's overkill. Can't we just, do something simpler? And it is a good detail, but it doesn't mean it can't go wrong. And this is a scenario where it has gone wrong. This is a remedial project. I think it was about 40 balconies that were redone. These balconies were tiered, so they were all open to the sky, getting direct rainfall. What happened here was this is a sheet membrane which has turned up and it's been turned into that reglet. It doesn't have the metal flashing, as is shown in the detail, but it is a sheet membrane terminated into the reglet. What happened in this scenario, and just ignore the overflashing, was this. Because that wall was exposed, water ran down the wall, behind the top of the skirting tile, and it ran straight behind the sheet membrane. And what we ended up with is this. So this was actually a block wall, so it was a little bit more porous than your average wall. If you can see this really dark color here, this block is completely saturated. And when we did remove that as part of a destructive investigation, we found sort of loose water to the touch. And the thing that actually made this one even worse is that as part of the remediation process, they'd identified that there wasn't suitable falls. So the entire area of the balcony had been topped up with a screed. Screeds are very porous and allow water to move quite freely. So as soon as it got behind this upturn, It ran everywhere below the waterproofing membrane, so much so that we had thought that the entire waterproofing system had failed, but the destructive investigation found that that wasn't so. It was all from these perimeter flashings. And my advice around this one is to take away, how do we prevent that sort of thing happening? Because it was a DTS solution, right? It's to think about it. I find a lot of our clients saying, we want to stick to the standard, we want to make sure it's DTS. And I'm like, okay, normally that sounds good, right? But I'll ask them, why do you want to do that? And they said, well, this is because it's easier. We don't have to think about it. If you do a performance solution, then we've got to do all this justification. I said, yeah, but isn't that a good thing? Don't you want to know that it's working? And the advice I'd give is, yeah, don't just take it for granted. It's considered to be one of the safest termination details, but it completely failed in this scenario and wasn't sufficient. Moving on to the next topic. Venturer's in a cavern, a deep cavern here. I don't know how he fell off the top of the cliff maybe. On one side he's got fire, on the other side he's got ice, and he's got to try and navigate this cavern. And what does this tie to? Well, it ties into our daily thermal cycle. And this is a little bit of a graph of that. I won't linger on this too long, but pretty much what it says is when the sun's up, things get hotter. And when the sun's down, things cool down a little bit. But the important thing to note here is that things actually do continue to heat up even after midday. You might fall into the trap of thinking, well, hey, once it's lunchtime or so, sun's starting to go down, so there's less thermal energy, things will start to cool immediately. That's not what happens. Effectively, the temperature keeps going up until around 3 or 4 in the afternoon. And that's a phenomenon called thermal lag, right? You might say, well, hey, we're not physicists, we're not that interested in thermodynamics. How does this actually help us? Well, I think it helps in a big way, because this is the most costly failure that I see during new construction installation with liquid membrane products. And I'll explain what it is. So, this is concrete surface, right? And this blue element here is moisture that might soak into the concrete, breathe in and out of the concrete. So during the day where it's heating up, that moisture is moving up out of the concrete, right? And then we go into our cooling cycle at nighttime, and then it goes back down. This fluctuates on how much, depending on seasonality and whatnot. So we go through this cycle here, right? And why is that a problem for us? Well, it's a problem because most construction sites start at 7 a.m. in the morning, right? People want to crack on with their work. So if you show up and you put down a waterproofing membrane across this nice concrete slab, as the moisture is rising, moisture and air are actually rising up and escaping out of the slab, well, what happens? This happens. Pinholing, bubbles, blisters, everything like this. So then we go back to our graph and we say, how can we use this knowledge of this cycle to stop this from happening? And the answer is that, see this blue line here, this is our heat increasing. Things expand when they heat, and when they cool, they contract. So our graph tells us right here, if we start our installation at around the 3 or 4 o'clock, right at that convergence there, then we're going to be right at the start, because no one wants to hang around till midnight to start their waterproofing. You're going to be right at the start of the cool down phase. So you should have nothing trying to force its way out through your waterproofing system, thereby mitigating any of that bubbling and pinholing. And if there was one out of all the things I'm talking to you about to sort of take the most note of, it's this one, because I still go to sites every week effectively where everyone has this idea, we're going to do this and this and this and get on there early and get out. And the same thing happens again and again, and it's just not worth it. When you look at, okay, how do I fix blisters and pinholes? I've got to recoat it. Huge amount of manual labor, huge amount of extra material. If you're worried about the overtime cost for doing it late in the day, it is an absolute fraction compared to what you're going to pay as the installer, as the builder trying to fix this after the fact. And on the topic of blistering, I have another phenomenon, which is somewhat rare and unique on its own, and it's a thing called osmotic blistering. And I'm going to do the best job I can at explaining this simply, but I'll start off with the definition. So osmosis is a process by which molecules of a solvent, water is a solvent, tend to pass through a semi-permeable membrane. A lot of waterproofing membranes are actually semi-permeable. They are not completely watertight. From a less concentrated solution to a more concentrated solution. Well, before we talk about that, what does it look like? This is what it looks like. These are large bubbles and blisters, and these are full of water. You can almost see the strain being applied here. If you were to pop one of these, water would spray out with quite a degree of force. And osmotic blistering develops in a few different ways, but effectively as the bubble grows, it applies pressure force and then delaminates it. So if the pressure force contained within the bubble is greater than the bond of the membrane to the concrete or the substrate, then it's going to continue to delaminate and continue to grow. There's a couple of different examples here of how these can grow or pop. And I'd say this is something definitely worth researching in your own time, but effectively, when we talked about moving from a less, I'll just go back here actually. From a less concentrated solution to a more concentrated solution, the most simple version of this that you'll see on construction sites is water on top of a membrane being attracted through osmotic force to the alkali in the concrete below. So it effectively, the concrete, the alkalinity and the chemistry of the concrete draws water through a semi-permeable membrane, and that's how these blisters are caused. So how do we stop these? Well, largely a lot of the suppliers are now aware of this for their polyurethane products and whatnot that are more susceptible because they have a higher vapor permeability. So how do we stop it? We've got a couple of answers here. So on those semi-permeable membranes, if you increase the thickness of them, it does bring down the permeability. So if you have a polyurethane membrane that you're allowed to install at 1 millimeter, maybe consider going to 1.5, 2 millimeters if you believe there's a risk of this. Shedding water effectively. Interestingly enough, where water is applied to a semi-permeable membrane and it's able to run to the drain and then dry out, this is not an issue. Where this occurs is where water is trapped, because it does take a little bit of a time for this force to draw it through. So if you have something like a flat protection board or even a large insulation panel, water will come down, get trapped between that and the membrane, and the osmotic force will have time to draw the water molecules through. And for any of those that are in the remedial space, I would expect that you have already, or you will start to see a lot of the rooftops that were done as a structure, waterproofing, insulation, and ballast buildup. I know I worked on quite a few 10 years ago. You'll find that when you pull up those insulation panels, it's going to be absolutely riddled with osmotic blisters. And that's the reason why. Back to our adventurer. Now we can see that he's making his way across this perilous gorge over a very narrow plank here. And what this has to do with us is another location on a building project where we see narrow strips of waterproofing very specifically. This is a step down, likely between an internal space and a balcony area, and it has been waterproofed. It's actually a double step down, by the way. You'll often see these as singles or doubles. And what's happened here is that waterproofing has been applied. Great, nothing going wrong here just yet. But to explain what's about to go wrong, I'm going to give you a couple of section details of that location we just looked at. So that double step down will either have a door sitting on it, or it will have some form of cladded wall or brick veneer wall, such as this scenario. So this is the strip of waterproofing that we've just seen. And the reason that this strip alone is done first, it's acknowledgement that when the walls and the doors go in is relatively early on. If we tried to waterproof an entire balcony before the walls go in, we're not going to get the floor finish installed for a long time. Waterproofing is going to be completely damaged and trashed, right? So it is a smart strategy. And it happens on almost every Class 2 project that I've been involved in. Now, where does this go wrong? Well, the thing which isn't actually very well shown in these details, and that's probably part of the problem, is that we have a requirement to move our water to the drains here, right? And what happens a lot of the time is builders very keen to get their doors and walls in. Waterproofer, get out here, do the strip. We'll worry about prepping the rest of the balcony later, right? Sooner or later comes around, and they have a look at it and they say, oh shit, we don't have falls to move water to our drain. It's going to pond right in front of this door here. Let's get a leveling compound or similar sort of product and let's build it up here so that water runs to the drain. That's in front of a door, obviously. Here's another one where it's in front of that brick veneer wall, and you can see it's been built up quite high because it's covered almost the entire first brick course, and it's just under the flashing there. And this is the situation we're left with. We now have our waterproofing membrane overlap, which was intended to be applied here. It's now completely covered by our topping. And so if we proceed with this, we end up building this. We've waterproofed this, water is able to enter, get on top of the topping, non-continuous waterproofing system, not going to be compliant because it's not continuous. And if this has any degree of exposure to water, it's not going to perform really well either. So then you ask, how do we prevent this, right? And it's 2 bullet points here, they both effectively say the same thing. Consider your sequencing thoroughly and apply the logic of solve it now rather than later. If you understand that there is a consequence of trying to solve it later, you're going to be motivated to solve it now, right? So it's as easy as that. And I'm hoping you're sort of realizing that there's a theme to all of this. The solution isn't costly or time-consuming. It's applying knowledge to consider and modify things early enough that they're not a costly or time-consuming problem. And with that being said, we're actually now moving into the final part. And I asked you earlier to have a bit of a think about what is an unknown known? How can you not know something? How can you not know something that you've already known? And the answer is we're complicated creatures as human beings, and we have choice. We can choose not to remember things or not to implement things. And that's really what this quadrant, or this last step of our journey, is about. And to really reframe that, we're going to go back to our adventurer one last time. You can see he's done well. He's got bags full of gold and other sort of jewelry, rubies and sapphires, and that's the actual exit over there. He's not far away, but something's caught his eye here. Biggest ruby he's ever seen. Of course, what's right in front of it? Massive skull on the wall. Anyone want to have a guess what skulls like that mean? Not very good, but he couldn't help himself. He was that close, he thought, what's the harm in it? I'll just do it, it's quickly, I'm so close to the finish line, just one more thing, it won't be a problem. And by choosing to ignore such a clear sign, our adventurer paid the ultimate price. And it's unfortunate because after all the things we went through, his journey didn't end because of a trap that he didn't know about. It was because of a warning that he chose to disregard. It's the most human part of our story today. We've done a lot of technical, but this last part is really about who we are as people and how we handle things. And I'll take it back to how you consider this on an everyday construction site. We walk past a pond of water, a large pond of water on a balcony. We know that's a red flag or a skull for something that's going to be a problem in the future. We see a abstract pipe penetration coming through that was fitted into a waterproof area after. We know it's not quite good enough just to chuck some sealant around it. We apply a waterproofing membrane. We know that it needs to take 72 hours at least in this climate to cure, but we've got our schedule. The schedule says we can only wait 24 hours to do a flood test. We do the flood test. The waterproofing membrane re-emulsifies and then gets covered, and it's never really cured. So these are the choices that we make every day. And I hope that from this, with the new knowledge and insights that you've received, not only from myself, but from all the other speakers that have already spoken, will spoke today, that you don't just take it on board, but you actually use it. You use it to solve problems. You don't disregard things, and you do it for the benefit of our industry. So I hope you've all enjoyed that. Thank you.